Hey guys, Assalamu alaikum warahmatullah. Problem number 52, chapter 23, Gauss law. Let me read out the problem. Figure shows a spherical shell with uniform volume charge density rho equal to 1.84 nanocoulomb per meter squared per meter cube. Inner radius A is equal to 10 centimeter and outer radius B is equal to twice A, that is 20 centimeter. What is the magnitude of the electric field at radial distances? Part A r equal to 0, part B r equal to A by 2, part C r equal to A, part D r equal to 1.5 times A, part E r equal to B, and part F r equal to 3 times B. So, we are given a charge system here. This is a spherical shell with an inner radius A, outer radius B, with uniform charge density, but only from A to B, not this is cavity, nothing there. Okay. We are asked to find our field at different points. Okay, at different points. So, this space can be divided into three parts. One is within the shell, in this cavity within the shell. The other is inside the shell from A to B. The other is outside the shell. Okay, so we'll find out field in all the three regions. One region we already know, remember from spherical symmetry, from Gauss law, we have done it so many times, that field inside the shell is 0. Okay, field inside the shell is 0. So, field inside the shell is going to be 0. So, we already know that. Now, some data is given, rho is 1.84 nanocoulomb per meter cube, A and B are given. In part A, we are asked to find out field at r equal to 0, distance equal to 0, that means here. So, that point is lying within the shell, so field is going to be 0. So, part A field is equal to 0 at r equal to 0. Part B, at r equal to A by 2, at r equal to A divided by 2. A divided by 2 is a point here. That's again a point lying within the shell. Okay, within the shell. So, field is going to be 0. Field inside the shell is 0. Okay. So, field is again 0. Then part C is r equal to A. So, that's a point here. That's a point here. If we approach that point within the shell, within this cavity, then field is going to be 0. Part C, r equal to A, field is going to be 0. And if we approach the same point from the shell, from within the shell, then we'll see field will again come out to be 0. The function is continuous there. We'll soon see that. So, this is part A, B and C. Field at all the 3 points is 0. Now, then we'll find out field somewhere here at 1.5 times A, and then here at equal to B, then outside this. So, we'll make use of Gauss law there. So, what I'll do is, in order to use Gauss law, I'll first find out charge enclosed by this Gaussian surface with the radius of r. So, I have drawn a spherical Gaussian surface there with the radius of r. We'll find out charge enclosed, then we can solve Gauss law. Charge enclosed is simply, since charge density is uniform, okay, charge density is uniform, so it's simply going to be charge density into volume. So, charge density rho, which is given to us value, we have that 1.84 nanocoulomb. 1.84 nanocoulomb is 10 to the power minus 9 coulomb per meter cube into volume. Now, volume is from A to R. Within A, there is no charge. Charge is only from A to B. Okay, charge only from A to B. And we have to find out charge not from A to B, from A to R, just from A to R. So, volume is simply outer volume minus this inner volume. Okay, so 4 by 3 pi r cube, outer radius r cube minus inner radius a cube. So, 1.84 into 10 to the power 9, or we can keep rho for a while, then we'll substitute the values. So, this is 4 pi rho divided by 3 r cube minus a cube. This is charge within this Gaussian surface of radius r. Now, we will solve Gauss law for this and find out the field at that point. Now, these are points lying within the shell. Now, from spherical symmetry, we know that field will be radially outward. This is a positively charged shell. So, field is going to be radially outward at all points. This is just from spherical symmetry. Then from, again, this is a spherical Gaussian surface. So direction of area is again radially outward, dA. Again radially outward. Here again radially outward, dA. So field and area are in same direction at all points. So angle between them is 0. So Gauss law, integral E dot dA is equal to Q enclosed divided by epsilon 0. Or I can write it this way, integral E dA cos of theta is equal to Q enclosed divided by epsilon 0. Well, Q enclosed we already know, we found that is here, 4 pi rho divided by 3 r cube minus a cube. And then on this side, the angle between field and area is 0 degrees at all points of the Gaussian surface. Now from spherical symmetry again, at all these points on this Gaussian surface, at all points of the Gaussian surface, here, field will be same in value. Again from spherical symmetry. Okay, again from spherical symmetry. Field at all points of the Gaussian surface will be same in value, in magnitude. Not within the Gaussian surface, not outside the Gaussian surface. We're just talking about the points on the Gaussian surface. Field is same. So field in this integral will be constant. So left hand side is over, E comes out, cos of 0 is 1, no need to write that. Integration of dA is A, total area, which is 4 pi r square for this Gaussian surface, sphere, 4 pi r squared is equal to Q enclosed divided by epsilon 0, so 1 by epsilon 0. Q enclosed is 4 pi rho divided by 3, 4 pi rho divided by 3, and then r cube minus a cube. So 4 pi and 4 pi will cancel out. 4 pi and 4 pi cancels out. So E r square will take downstairs here. So E is equal to r square will take downstairs. So this is rho divided by 3 epsilon 0. Okay, rho divided by 3 epsilon 0. Rho divided by 3 epsilon 0. Then r cube minus a cube, will divide this r square there. So we'll have r here, r cube divided by r square is just r, minus a cube divided by r square. Was it minus or plus? Minus. A cube divided by r squared. So this is field inside the shell. Inside the shell. Between A and B. Okay, so this is between A and B. That is to say, A is less or equal to R is less or equal to B. Okay, so this is the formula for the field we have found. Now, I'll again go to part C where R is equal to A. We have done that here, somewhere here. Yes, R is equal to A. That means at a point on the surface, inner surface of the shell. So here we went to the surface from inside, so field was 0. Field was 0 because at every point field is 0. Now we'll approach the same point from within this shell and see if field is again 0 or something else. So let's use it here. Part C. R equal to A. If R is equal to A, this becomes A squared, 1 gets cancelled out, so 1 remains there, A minus A is 0, so everything becomes 0. So field is 0. So irrespective of whether you approach the surface from the cavity of the shell or from within the material of the shell, field is 0 at the inner surface, meaning field function is continuous there. Then part D, at R equal to 1.5 times A. We'll find out at 1.5 times A. Is it that? Yes. 1.5 times A, which is to say 3 by 2 times A. At 3 by 2 times A. So we'll use R equal 3 by 2 A here in this equation and find it out. So E is equal to rho divided by 3 epsilon 0. R instead of R we'll write 3 by 2A. Minus a cube divided by r square, remember r square is there, r square, r, 3 by 2a, and then r square is there. So 3 by 2, a like with the square, so 3 square is 9, 9a square, divided by 2 square is 4, 4 will go upstairs. A square, this gets cancelled out, so we have E is equal to rho divided by 3 epsilon 0, 3 by 2A minus 4 by 9A. We can take this A common, so we have rho divided by 3 epsilon 0, 3 by 2 minus 4 divided by 9 times A. So this becomes 9 into 3 is 27, rho divided by 3 epsilon 0, 27 minus A divided by 18 times A. So E is equal to 27 minus 8 is 19. So 19 rho divided by 18 into 3, okay, 8, 3, 24, 54, epsilon 0 is there, okay, epsilon 0 is there, then this A. So 19 at this distance at R equal to 1.5 times A, 19 rho divided by 54 epsilon 0 A. Okay, now let's substitute the values and write down what the field is equal numerically. So E is equal to 19, rho is 1.84 nanocoulomb, 1.84 nanocoulomb, so 10 to the power minus 19 per meter cube. Then we have A, remember A was I guess 10 centimeters, yes 10 centimeters, so 10 into 10 to the power minus 2 divided by 54, epsilon 0 is 8.85 into 10 to the power minus 12, okay, 8.85 into 10 to the power minus 12. So this is what we have to work out. I have already done that. This comes out to be 7.32. 7.32 Newton per coulomb. This is field at a distance of 1.5 times A. Okay, 7.32. 7.32. So 7.32. This is not minus 90. 1.84 nanocoulomb. That's minus 9. Just minus 9, not minus 19. Minus 9. So just to convert nanocoulomb to coulomb, 10 to the power minus 9. So this comes out to be 7.32 Newton per coulomb. Newton per coulomb. Now next part is we have to find our field at R equal to B. Okay, at R equal to B. That means at the outer surface. Okay, somewhere here at the outer surface at R equal to B. So this is part E at R equal to B. Remember B is twice A. Okay, B is twice A. So we have to find out field at R equal to twice A. So let's substitute instead of R, we'll substitute twice A here. So rho divided by 3 epsilon 0 twice A cube divided by this thing. So E is equal to rho divided by 3 epsilon 0 R, which is twice A, minus A cube divided by R square, that is 4A square. Okay, 4A square. So something is cancelled, A square, and this will get cancelled out. So we have A divided by 4 here. This is rho divided by 3 epsilon 0. 4 into 2 is 8. 8 minus 1 is 7. 7A divided by 4. So this is 7 rho A divided by 4 into 3 is 12. 12 epsilon 0. This is field at the outer surface. Okay. So let's substitute the values. Let's substitute the values. E is equal to 7. Rho is 1.84 nano, so 10 to the power minus 9 coulomb per meter cube. Then we have A was 10 centimeters, so 10 into 10 to the power minus 2 divided by 12 epsilon 0, so 12 into 8.85 into 10 to the power minus 12. So this is what we have to work out. I have already done that. This comes out to be 12.1 Newton per coulomb. 12.1 Newton per coulomb. This is field at the outer surface. Okay, this field at the outer surface. Then we have to find out field at a point lying outside the shell. So first we will find out an equation for the field there. So now I am considering a Gaussian surface, Gaussian spherical surface lying outside the shell with radius r. Now note that all of this space within this Gaussian sphere is not having charge. Charge is only in this part. In this part. with inner radius A and outer radius B. Okay, inner radius A and outer radius B. We have already found an equation for charge within a sphere, within a shell of radius r, that is, I guess here, 4 pi rho divided by 3 r cube minus a cube. R was the outer radius of that shell which we are considering. Now that we have to find out all the charge of the shell, that means our outer radius is this time b. So instead of r, we'll write down b. Okay, instead of r, we'll write down b. So we'll have b cube minus a cube. Okay, b cube minus a cube. Or we can simply write density into volume. Volume is simply outer volume minus the inner volume. Outer volume is 4 by 3 pi b cube minus 4 by 3 pi a cube. So same thing. So charge enclosed this time, charge enclosed is rho 4 by 3 pi outer radius cube b cube minus inner radius cube a cube. Now b is twice a, remember that, twice a. So this is 4 pi rho divided by 3. 2b cube, 2 cube is 8, so 8 a cube minus a cube, so that is 7 a cube. 7 into 4 is 28 pi rho divided by 3 a cube. Okay, so this is charge enclosed. This is charge enclosed. Then so let's solve Gauss law for this now. Again, from spherical symmetry, field at all points will be radially outward and same in magnitude on this Gaussian surface, and this is field, and area direction is again radially outward, so they are in the same direction. So number one, field and area are in the same direction at all points of the Gaussian surface. Number two, field is same in magnitude at all points of the Gaussian surface, just from spherical symmetry. So Gauss law now, integral E dA cos of theta is equal to Q enclosed divided by epsilon 0. So E comes out, cos of 0 is 1, integration of d is 4 pi r square is equal to 1 by epsilon 0. Q enclosed is 28 pi rho a cube divided by 3. 28 pi rho a cube divided by 3. Okay, divided by 3. So something gets cancelled out. 4 into 7 is 28. Pi and pi cancels out. R square goes downstairs. So E is equal to, what are we left with? 7 rho a cube. 7 rho a cube divided by 3 epsilon 0. 3 epsilon 0. And then this R square comes downstairs. Okay. So this is field at a point lying outside this sphere. Outside this sphere. Now, field is inversely proportional to r square. This is, we already know this for a spherical symmetry. For points lying outside the shell behaves like a point charge located at the center. We could have directly written gamma q divided by r square, but then we don't know q, total charge. Okay, so this is what is total charge. Instead of q, we have this thing. So we can also put it in terms of the total charge q if we write. In this case, I have written it in terms of rho. Okay, in terms of charge density rho. So this is our field outside. Now we have to find out field at 3 times b. 3 times b. So this is F, I guess, part F. Yeah. At r equal to 3 times b. Remember, b is twice a. So 3 into 2 is 6. 6 times a. Field is 7 rho a cube divided by 7 rho a cube divided by 3 epsilon 0 r squared. 3 epsilon 0, instead of r we have 6a squared, so 6 squared is 36, a squared. A square and 2 gets cancelled out, so we have 7 rho a divided by 36 into 3, 6 into 3 is 18, 339, 108 epsilon 0. Yeah. So this is our field at 6 times a or 3 times b. 7 rho a divided by 108 epsilon 0. Let's substitute the values. So E is 7. Rho, remember, was 1.84 nanocoulomb. So 10 to the power minus 9 coulomb per meter cube. A is 10 centimeters, so into 10 to the power minus 2 divided by 108, epsilon 0 is 8.85 into 10 to the power minus 12. So this is what we have to work out. I have already done that. This comes out to be 1.35 Newton per coulomb. Okay, 1.35 Newton per coulomb. So this is field outside it. Yeah, that's it. That's all we're asked to find out. Fine, that'll do for this session.